For section 5.3, we're going to take a look at something called the inclusion-exclusion principle and binomial theorem. And so this whole thing that says inclusion-exclusion principle, it has to do when we take the union of lots of sets and we would like to know the actual number of elements within that union. Particularly when we have sets that are not mutually disjoint, and that is sets that have elements in their intersection. And so we have to watch out for counting those things, so we don't count things more than once. If in the union if in the intersection they actually have something in common. So it can cause some problems. There's in words here the basic principle of how to do this. It says first off, to calculate the size of a set A1, union set A2, union with all the way up to another set AN. What we're going to do is calculate the size of all possible intersections from A1, A2 up to AN. Add the results obtained by intersecting an odd number of the sets, and then subtract the results obtained by intersecting the even number of sets. So here's an example of how this goes for, say, n equals 3. We had 3 sets. We had A1, union A2, union A3. We want to calculate the number of elements in the union of those 3 sets. So the inclusion-exclusion principle says this is going to be equal to, first off, we take the number of elements in A1 plus the number of elements in A2 plus the number of elements in A3. And when they're mutually disjoint, this is all we really have to worry about. But in general, we have to continue on here by taking and subtracting, intersecting the even number of sets together. So by that I mean intersecting 2 at a time. So A1 intersect with A2, and then we take the intersection of A1 and A3, so 2 at a time, and then the intersection of A2 and A3. Now I'm counting those up, I'm going to add them together, and then that gets subtracted as a whole. That's why I'm putting it here in parentheses. And then also what we're going to do is add to this the results obtained by intersecting an odd number of sets at a time. So if I take A1, intersect A2, intersect A3, so 3 at a time, an odd number, then add that to it, we get this whole inclusion-exclusion principle for 3 sets at a time. In our first example, it says count the number of integers from 1 to 2000 divisible by 9 or 11, by 9, 11, or 13, or by 9, 11, 13, or 15. Okay, so what we're going to use in this example here is the notation of the set dk is going to be the set of all n in the set from 1 to 2000 such that n is divisible by k. And so the way we can figure out how many elements are in this set is by doing the formula we had from the very first section, 1.1. The number of integers divisible by k, or the number of multiples of k between 1 and 2000, is 2000 divided by k, and we take the floor of that. So that will tell us how many elements are within that set of numbers between 1 and 2000 divisible by k. So now we're going to go through here first the number of elements from D9 union with the number of elements from D11. We want to count up the number in that union. So the inclusion-exclusion principle says what we're going to do is we're going to take the numbers in D9, number of elements in D9, plus the number of elements in D11, minus, we have to intersect them 2 at a time, so D9 and D11. And that's all we have to do here since we only have 2 sets total. So if we calculate the number of elements that are in D9, or the number of integers here divisible by 9, we would get 222. And if we do the number of integers divisible by 11, it would turn out to be 181. Now, if we want to know the number of elements in the intersection of these two sets, basically it's the number of elements divisible by both 9 and 11. We can actually come up with that here. I'll write this off on the side. The way we could do that is if it's divisible by 9 and 11, it'll be divisible by 99. So we could figure out the number of integers between 1 and 2000 divisible by 99 here. That comes out to be 20. So we have 222 plus 181 minus 20. So they are equal to 383 integers between 1 and 2000 divisible by 9 or divisible by 11. Okay, it's going to get a little bit longer the more that I go here, but I'm going to apply the inclusion-exclusion principle to make it work. Here we're going to find the number of numbers divisible by 9 or 11 or 13. So the number of elements in the union of those three sets. Okay, so go through the principle of inclusion-exclusion. We take the number of elements in the first set plus the second plus the third. Okay, and then I have to subtract the number of elements in intersection, but 2 at a time. So we can do that with D9 intersect D11, also D9 intersect D13. And also we can do D11 intersect with D13. Those are the different ways we can put those together 2 at a time and intersect them. But then we have to add together the intersection of them all at once, 3 at a time. Okay, so I'll work the numbers out here. I'll write the numbers out for each of the individual things. The number divisible by 9, we figured that out to be 222, and then 181. And then the number divisible by 13 is 153, subtracted by the intersections. So we figured out 20 for 9 and 11. If we do it for 9 and 13, we can get 17. And for 11 and 13, we can get 13. And then divisible by all three, if we check that out, we'd actually just have 1. So this all comes out to be 507. Okay, now let's apply the inclusion-exclusion principle for the union of 4 different sets for D9, D11, D13, and D15. So this will be equivalent to saying how many are divisible by 9 or 11 or 13 or 15. So I'm going to kind of write down words with the inclusion-exclusion principle would have us do. We're going to count up the number in here 1 at a time. And then we're going to subtract the number in the intersections 2 at a time. But we're going to add the number from the intersections 3 at a time. And then we're going to subtract the number in the intersections 4 at a time. Okay, so, and the reason why I'm doing this again is inclusion-exclusion. It would basically, we do odd, we add the odds together, and then we subtract the even at a time, plus the odd at a time, plus the even when we take them together and intersect them, even number of sets at a time. Okay, so it's going to be kind of long, so I'll try to make it look as clear as possible here. First off, we'll do them one at a time. So we're going to do D9 plus D11 plus D13 plus elements in D15. Okay. Now we're going to subtract the intersections here, 2 at a time. So we have to put together D9, intersect with D11, D9, intersect with D13, D9, intersect with D15. We have intersect D11 with D13. We got to do D11 with D15. And then finally, we can do D13 intersect with D15. Okay, those are all the intersections. And now we'll add with that the intersections. That was 2 at a time again. This will be now 3 at a time. So D9 intersect with D11, intersect with D13. We'll add that. And we'll be adding now the odd number at a time here, 3 at a time. 9, 11, and 15. 9, 13, and 15. And then 11, 13, and 15. And then those are all those, and then we need to subtract the number of intersections of 4 at a time. So 9, 11, 13, and 15. Okay, so I'll write out the numbers. Basically, we can go through and do the calculations for each individually. But it turns out we'll have 222 plus 181 plus 153 plus 133 from the first 4. And then the intersections 2 at a time, we subtract 20 and 17, 44, 13, 12, and 10. And then from the other intersections, we have 1 and 4 and 3 and then 0. And then finally, the last number is 0. So when we put these all together, we get 581. And now what we're going to discuss is something called the binomial theorem, also called the binomial expansion sometimes. And so for real numbers a and b and n in the natural number set, we have this summation which can give us a plus b raised to the nth power. So this is handy when expanding binomials raised especially to higher powers. So I'll kind of go through the process here. It says the summation r equals 0 to n of n choose r, a to the r, b to the n minus r. So this constructs the individual terms in the expansion, and they're all added together by the summation. So when we look at this first example here, which says a plus b raised to the 5th power. So from the binomial expansion, this would be the summation r equals 0 to 5. Of 5, choose r, a to the r, b to the 5 minus r. So what I'm going to do is use this inner form to construct each term and then add them together with our summation. So the first term, since r is 0, starts from 0, be 5, choose 0, a to the 0, b to the 5 minus 0. That's the first term. The second term is 5, choose 1, a to the 1, b to the 5 minus 1. The third term would be 5, choose 2, a to the 2nd, b to the 5 minus 2. The next term would be 5, choose 3, a to the 3rd, b to the 5 minus 3. Then we're going to have 5, choose 4, a to the 4, b to the 5 minus 4. And then our last term would be 5, choose 5, a to the 5th, b to the 5 minus 5. Okay, and so we just have to do the calculations here. 5, choose 0 is 1, and a to the 0 is 1. So the first term is just going to be b to the 5th. 5 choose 1 is 5. So we're going to have 5ab to the fourth. And then 5 choose 2 is 10. So it'd be 10a squared b to the third. 5 choose 3 is 10. And so that'd be 10a cubed b squared. 5 choose 4 is 5. So that's going to be 5a to the fourth b to the first. And 5 choose 5 is 1. So that's going to be a to the fifth. And then b is not going to be there since it's going to be b to the 0. And that's just 1. So that's how this whole binomial expands by the binomial expansion. Okay, now we're going to look at the binomial expansion for x minus 4y raised to the fourth. And let's make this look like our expansion from kind of up above where we had a plus b. Let's make it x plus negative 4y. And so the binomial expansion summation would go the summation r equals 0 to 4 of 4 choose r, x to the r, negative 4 to the 4 minus r. Our first term would be 4 choose 0, x to the 0, negative 4y raised to the 4 minus 0. The next term would be 4 choose 1, x to the first, negative 4y raised to the 4 minus 1. And then we'd have 4 choose 2, x squared, negative 4 raised to the 4 minus 2. And we have 4 choose 3, x to the third, negative 4y raised to the 4 minus 3. And then lastly, we'd have 4 choose 4, x to the fourth, negative 4y raised to the 4 minus 4. 4 choose 0 is 1, and x to the 0 is 1. So basically this first term is going to be 4y raised to the 4. And then we're going to have 4x, negative 4 raised to the third. And then we're going to have 6x squared, negative 4 raised to the second. And then 4x cubed, negative 4y raised to the first. And then we're going to have just x to the fourth here at the end, since 4 choose 4 is 1, and negative 4y would be raised to the 0 power. So that's just x to the fourth. So when we raise the negative 4y to the fourth power in the first term, it's going to be 256y to the fourth. When we multiply the numbers together in the next term, it's going to be negative 256x y to the third. Then we're going to have plus 96x squared y squared. Then minus 16x cubed y. And then finally plus x to the fourth. Now the last thing we're going to look at here is kind of another counting situation here. It says ways of placing objects in boxes, especially when the objects are identical and the boxes are distinguishable. And so it has this formula here, two different ways of writing it. It says n plus k minus 1 choose k minus 1 is equal to n plus k minus 1 choose n. And that's the number of ways that n identical objects can be placed into k distinguishable boxes. The number of ways of selecting a set of n objects of k distinguishable types allowing repetitions is also the same as this. So the first situation I'd like to show is how many ways can 10 identical marbles be placed into 5 distinguishable bags. So in this example, we have 10 marbles. That's the number of objects, and that's going to be the n. And k is the number of boxes or bags, and so there are 5 distinguishable bags. And so by our formula up above, n plus k minus 1, choose k minus 1, would be 10 plus 5 minus 1, choose 5 minus 1, which would be 14, choose 4. And that calculation, again, our formula for that is 14 factorial divided by 4 factorial times 10 factorial. And that comes out with 1001. Now, on example 4, it says, in how many ways can 15 indistinguishable fish be placed into 5 different ponds so that each pond contains at least 1 fish? So let me kind of visualize this one a little bit. We have 5 ponds here. In each pond, we're going to put 1 fish. And so there will be 10 fish remaining. And so the remaining 10 fish can be placed into the pond similar to what we did in the last example, actually. So basically there are n equals 10 indistinguishable objects and k equals 5 different locations to place them, boxes or pools or ponds or bags. So the formula for this would go 10 plus 5 minus 1, choose 5 minus 1. And so we had the 14, choose 4, and that's 1001. Now lastly here it says, and how many ways can 10 coins be selected from an unlimited supply of pennies, nickels, dimes, and quarters? So this is kind of similar to what we were doing in the last ones, but we're kind of going the other way around. We're selecting from 4 different groups, and there are 10 coins to be selected. So this works out to be n equals 10 indistinguishable coins, and there are k equals 4 for the different types of coins. So distinguishable coin types. So I'll do the same calculation here, n plus k minus 1, choose k minus 1. So 10 plus 4 minus 1, choose 4 minus 1. 13, choose 3. So 13 factorial divided by 3 factorial, 10 factorial. And so that would equal to 286 ways.